Welcome to General Chemistry Mini Lecture Series, Lecture 10, Empirical and Molecular Formula. That's what we are going to talk about in this lecture. A chemical formula is comprised of element symbols and numerical subscripts. So the formula shows the type and number of each atom present. Let's see, we have those few. Okay, they are all called chemical formula. Mainly there are two types of formulas. So one is an empirical formula, and the other one is actually molecular formula. Okay, so empirical formula that actually indicates the relative number of atoms of each element in a molecule or compound. In other words, it uses the smallest whole number ratio, the smallest whole number ratio possible. So that's the empirical formula. Molecular formula actually shows the actual number of atoms of each element in a molecule. Structure formula basically, we just use lines to represent covalent bonds and show how atoms in a molecule are connected. Yeah, so let's work on molecular and empirical formula. So we have the chemical name, and then the first one is molecular formula, then the last column is empirical formula. Benzene, so the gasoline our course uses every day that contains a low concentration of benzene is very toxic. Molecular formula, 6 carbon and 6 hydrogen, C6H6. The empirical formula, you see, if you divide the subscripts by 6, you get 1 for carbon and 1 for hydrogen. So therefore, this CH is the empirical formula for benzene. Carbon dioxide. So carbon's subscript in this one is 1, even though it does not show. So therefore, in this case, molecular and the empirical formulas are the same. Glucose, here's the molecular, and we divide all of the subscripts by the lowest subscript or by the smallest number, which is 6 in this one. So then you have CH2O, that's the empirical formula for glucose. Oxalic acid, divide everything by 2, you have CHO2. Okay, we just talked about the structural formula in the previous slide. You see, if you just look at the chemical formula or the molecular formula, it really doesn't show how atoms are connected. You could not see actually carbon, each carbon connects to one oxygen, and that's the double bond. There's no way you can see it. But here, with the structural formula, you can see a little bit more details. Still, the structural formula is still not the actual model for oxalic acid. Okay, here looks like it's just 180 degrees. It's a line structure. As a matter of fact, it's not. You see hydrogen, this small one, that's hydrogen, and then oxygen, the right one is oxygen. Yes, here's linear, but to the first carbon from oxygen, you see, it assumes a bent structure. Okay, and then carbon-carbon, okay, that's of course you can call that linear, and then let's change direction again. Okay, so we'll talk more about those molecular shape. That's actually called molecular geometry. So we'll talk about more about this in much later chapters. Let's work on another practice. Find the empirical formula for each of the following. Okay, so octane. When we add fuel, we always try to find out which octane number should we use, all right? So 87 is the common one. And what is octane? So basically, that's the one of the major ingredient. So in gasoline, and that's C8H18, okay? So let's take a look what the empirical formula should be. We divide everything by 2, then we'll have C4H9. And obviously, 4 and 9, that's the smallest whole number ratio already. So therefore, C4H9 is the empirical formula for octane, while C8H18 is the molecular formula for octane. Second one, the ionic compound that has 2 iron ions, iron 3, which means that's 3 positive charges for every 3 oxide ions. Oxide, so that's O2 minus, all right? And then if you put them together, each iron ion, that's a 3 plus. 3 plus times 2 on the cation side, that's positive 6. Then each oxide carries negative 2. Therefore, negative 2 times 3, that's negative 6. Positive 6 plus negative 6, the overall charge for this ionic compound is 0. So you need to remember, for all ionic compounds, their formulas are always empirical formulas. Okay, they are already in the simplest ratio, whole number ratio. Caffeine, that's the structural formula, and the molecular formula, let's divide everything by 2. This is the empirical formula for caffeine. Well, this is the molecular formula for caffeine, and this is the structural formula for caffeine. Ethylene glycol. Okay, so you see you have 2 carbon, and then we have the little gray ones are hydrogens, 2, 3, another 3, that's H6, and then the 2 red ones, they are oxygen, O2. So that's the molecular formula. Divide everything by 2, we have C1, H3, O1, all right? Of course, for subscripts, if it's 1, you just don't write it down. Let's keep working on molecular and empirical formulas. Okay, ionic compounds, I already mentioned. All ionic compounds, they are already in the empirical state. So it's already the simplest one. Let's work on one more problem. What is the formula for the ionic compound that has 1 calcium ion for every 2 chlorides? 1 calcium cation for every 2 chloride. Covalent compounds, of course, we are talking about nonmetals. Let's take ethanol as the example. Okay, so 2 carbon, and then 6 hydrogen, and 1 oxygen. So therefore, the molecular formula, we can write that down. That should be 2 carbon, 6 hydrogen, and 1 oxygen. So that's a molecular formula. And as you can see, that's actually also the empirical formula, because that's already in the smallest whole number ratio. Okay. Yeah. So now, when we really talk about the molecular formula, actually, if you write the molecular formula this way, CH3, basically that means this group, this methyl group, one carbon right here, and then 3 hydrogens. And then next is connected to this CH2, all right? So ethyl group, so we are talking about this one. And then that's connected to the hydroxyl group, OH group. Okay? So actually this molecular formula, this one serves better in terms of, knowing the structure of ethanol. And then sometimes people just write down C2H5. C2H5, C2H5 group, ethyl group. Okay, that's why the shorthand formula is ET. Okay, ETOH. That's even better. Yeah. Then the empirical formula, as I mentioned, this is molecular formula, but also empirical formula is basically just tell you the number. It does not really show the actual arrangement, the actual connection among the atoms. So that's a little bit more understanding to the molecular and the empirical formulas. Okay. Now the guidelines for determining an empirical formula from experimental data. So there are 5 groups. I will not spend too much time here because I'm going to use exactly those 5 steps to work on one example so that we can better understand those guidelines or those rules. Okay, very briefly. Number 1, typically the mass percentage of each element is given. Okay, and we can just simply assume that we have 100 grams. Then the mass percentage becomes grams. Step number 2, we convert grams to moles using molar mass. I'll tell you what molar mass is. Number 3, write a so-called pseudo-formula. Pseudo-formula allows non-whole number as subscripts. So they are not a real formula. That's why we call them pseudo. Step number 4, divide all of those subscripts by the smallest number of moles. And then number 5, you will try to change those mole ratios to whole number ratio by doing some simple math. Okay? Yeah, let's work on this problem. So we have benzoic acid, and that's easily found in soft drinks, also in fruits. So it contains 68.85% carbon, 4.95% hydrogen, 26.2% oxygen. If you add them together, that should be 100%. Now, what is the empirical formula of benzoic acid? Start with number 1. Convert percentages to grams. Okay? Just assume you have 100 grams, then those percentages just simply change to 68.85 grams. That's what I have here. And then 4.95 grams, that's hydrogen, and the first one is carbon. And then oxygen, again, you change that percentage to grams. Okay, that's what you do. Very simple. But if you already have grams given in the problem, you just eliminate, ignore step number 1. Now, molar mass. Okay, what is molar mass? Molar mass for element, we'll start with that first. Molar mass of an element is simply the atomic mass of that element in grams. And where do you find atomic mass from? Periodic table. Any of the periodic table, any copy of periodic table. Lithium, 6.941. And the atomic mass is in AMU. Now, the molar mass for lithium is 6.941 grams. That's it. So the same number, but only the units change. That's molar mass of element. Okay, now as we can see, carbon, if we look at carbon, that's 12.01 AMU. That's atomic mass. Then the molar mass is the same number, but in grams. And you do the same for hydrogen and oxygen. You can easily get those values from a copy of periodic table. Okay, now what does the molar mass mean? Okay, let's say the atomic mass means one carbon atom weighs 12.01 AMU. But the molar mass means 1 mole of carbon atoms weighs 12.01 grams. Okay, so that's what it means. It's the mass of 1 mole of the substance. That's molar mass. Atomic mass is the mass of 1 atom of that element. So that's a difference. Now, let's still keep working on this step. Okay, I change the value from given to known because, those grams, they were not given directly in the question. Remember that? So that's what we kind of converted to. But nonetheless, they are known now. Okay, and what do we need to find out? We need to find out the empirical formula. In order to find out the empirical formula, we have to find out the subscripts of each element. The concept plan, first we convert from grams of each of the element to moles of each of the element using molar mass right here. And then we will convert further to the mole ratio. Okay, so basically we divide all of the moles using the smallest mole value, and then we should be able to get the empirical formula. So we should be able to find that out. Okay, let's calculate the moles of each element. Carbon, we have this many grams, and then we are converting from grams, put that on bottom, and converting to 2 moles, put that on top. So that's dimensional analysis, all right? And 12.01 is the molar mass. Molar mass means, again, is the mass in grams of 1 mole of that substance. So in this case, the substance is just carbon atoms. Now we have this many moles of carbon. And as you can see, grams are cancelled. We do the same for hydrogen and for oxygen. So now we have the number of moles for each of the 3 elements. What do we do next? We just simply write the pseudo-formula. Just use the mole number as subscripts. Step number 4, divide all of the subscripts or the number of moles by the smallest number of moles. Smallest number of moles in this case here is 1.638. Okay, so for carbon, we got 3.5. For hydrogen, we got 3. And for oxygen, we have 1. Now, we can have a second pseudo-formula, a better one. At least we have two whole numbers, and now carbon is the only one that still is not in a whole number. We have to convert that to a whole number. Okay, so we have a 3.5. Doesn't matter whether it's 1.5, 2.5, or 9.5. In order to convert that 0.5 to a whole number, all right, so anything of 0.5, we need to times that number by 2. 3.5 times 2 equals 7. 2.5 times 2 equals 5, and so on and so forth, all right? And if you have other ratios like 0.33 or 0.67, times by 3, and if you have ratios like 0.25 or 0.75, just multiply by 4, and they all will be converted into a whole number, okay? So, of course, in this question, we have to multiply carbon's mole ratio by 2, but if we do that for carbon, we have to do that for hydrogen and oxygen. No discrimination. Okay, for carbon, we have 7 carbons now. Hydrogen, 3 times 2, we have 6. Oxygen, we have 2. And now let's see. C7H6O2, that's the simplest whole number ratio, or the smallest whole number ratio. Therefore, this has to be the empirical formula for benzoic acid. And as a matter of fact, this also happens to be the molecular formula. Just like water, H2O, H2O is both the molecular and the empirical formula of water. Okay? Yeah, now let's further talk about the relationship between empirical and molecular formula. The molecular formula is a multiple of the empirical formula, all right? So if we know the empirical formula and the molar mass, we should be able to determine the molecular formula using this equation. Molar mass of molecular formula over molar mass of empirical formula, because the molar mass of molecular formula should be at least equal or higher than that of the empirical formula. So therefore, we should always have a multiplying factor. We call that n. If n equals 1, then molecular formula equals empirical formula. Let's work on a problem. A compound has an empirical formula of CH3 and a molar mass of 30.07 grams per mole. Find the molecular formula. Okay, what is given? The empirical formula is given, and the molar mass of the molecule. What do we need to find out? We need to find out the molecular formula. Okay? Relationship or equation. We just use the equation we just learned from the previous slide. Now let's try to solve it. Molar mass of the empirical formula. First, we have to find that out. We know the empirical formula is 1 carbon. Okay? That's why we have 1 here. And then times the molar mass of carbon. That's 12.01 grams per mole. Then plus 3 hydrogen times the molar mass of each hydrogen. Then we found out 15.03 grams per mole. That's the molar mass of empirical formula. Okay? So therefore, n, we are applying this equation now. N equals the molar mass of molecular formula, that is given 30.07, all right? Then divided by the molar mass of the empirical formula, which we just found it out right here, then n is 2. Okay, good. So we know the multiplying factor is 2, and we know the empirical formula is CH3. We just multiply the subscript in the empirical formula by 2. Okay, carbon has 1, then 1 times 2 equals 2. That's why here is C2. Hydrogen has 3. There are 3 hydrogen atoms in this empirical formula. Multiplied by 2, we have 6. C2H6. That's the molecular formula. We can check it. The molar mass of the calculated formula is actually in agreement with the given molar mass. What does it mean? You can just use a copy of periodic table to find out the molar mass of C2H6. Okay, 2 times the carbon's molar mass, so 2 times 12, and that's about 24. And then 6 hydrogen, 6 times 1, that's about 6. Then that gives us about 30. You see, just double check on that. So it makes sense. Then it means our solution should be correct. Okay, this is the end of lecture 10 quiz questions. I'll quickly work on number 1. Which of the following is an empirical formula? Obviously, this one is not in its smallest whole number ratio, so therefore it's not. That should be out. A, so should be out. Okay, B, C1H4, that's in the smallest whole number ratio. Okay, we keep this so far. C, C2H4, again, can be divided by 2. That's out. And then D, C2H2, can be divided by 2. So therefore, B should be the correct answer. Okay. There are a few more end of lecture quizzes, and you guys should work on all of this. And of course, many more homework problems and from other sources. Okay, this is lecture 10, and I will see you guys in lecture 11.